Now we continue our discussion. This is the fourth part of a series of discussions. In the third part of the discussion, we show that we chose the second position as the new motif starting position for the first sequence. So this is our first sequence, and the second position was chosen as the was sampled randomly sampled to be the first position for our motif. Now, once we have this, the next thing we do is we repeat the whole process, but this time we use a new sequence for sampling. Remember, in the previous discussions, we chose the first sequence as the sequence for sampling, and then we use the three remaining unchosen sequences as the sequences for building the probability tables used to sample the first sequence. But now that we're finished with that, and we chose the second position as the new motif starting position for the first sequence, the next thing we do is we choose a new sequence for sampling. In this case, for simplicity, we simply iterate through each of these, and the next one in the iteration is the second sequence. So now we choose this second sequence here as the sequence for sampling, and so we try to isolate the second sequence, and then the remaining unchosen sequences, in this case the first sequence, the third sequence, and the fourth sequence, these are your unchosen sequence. We use these three sequences as the sequences to build the probability tables, and once we build the probability tables, we just follow the whole process again. Once we're finished with the probability tables, we try to find a new motif position for the second sequence. So we try to sample for a randomly sample for a new motif starting position for this second sequence here, just as we did for the first sequence. So here, once we're finished with the second sequence, we do it for the third sequence. We repeat the whole process for the third sequence, and then once we're finished with the third sequence, we repeat it for the fourth sequence. So we repeat the whole processes. We iterate the whole process through each of the sequences for which we want to obtain the motif positions in. And once we iterate through all of these sequences, we actually proceed with a continuing process of repeating the whole process all over again, and eventually we hope that we would obtain some kind of convergence, meaning that the positions we obtain for the first sequence, for the second sequence, for the third, and for the fourth, somehow they stop moving, and when they stop moving, we say that convergence has happened, and these are probably the best motif positions for the motifs. So remember, at the start we were trying to look for the positions where the Gattaca positions are located, the Gattaca motif are located. So if we look at this sequence here, this motif position here has a motif that appears to follow the Gattaca sequence, Gattaca, your Gattaca sequence, and the only difference is the first one here, and then the fourth one over here. So here we have two deviations from the Gattaca motif. In the second sequence, you have one here, and then you have another here. So we have two deviations from the Gattaca consensus motif. And then for the third one, we have one here, one deviation here, and then we have another deviation here. So we have two deviations again for the third, and then for the fourth we have one here, one deviation here, and then another deviation here. So for each of these sequences, these motif positions give deviations of at most two residues. So these positions, they show the Gattaca sequence or the Gattaca motif more or less quite well, except for two residue positions at most. Now, the Gibbs sampling method, in summary, is a way to obtain uh, the positions of a certain consensus motif in a given sequence, in a given series of sequences. But the problem is with the Gibbs sampling method is that if the motif um, is weakly manifested in each of the sequences, meaning some sequences would have for instance, the Gattaca motif, but they would have several deviations from it. So the motif is existent, but it's not very clearly shown, meaning that it does not, the motif in some of the sequences may not um, very well match the consensus motif. And so if you have some sequences which manifest the consensus motif weakly, then you would need to have very large sets of sequences in order to obtain some kind of statistical significance for the motif positions. The next thing is the Gibbs sampling motif is probabilistic in nature, and because it's very probabilistic in nature, it's very heuristic. Uh, you don't have a guarantee that you would obtain an optimal value, meaning a convergence answer wherein each of the motif positions give you the true positions of the uh, motif positions in each of the sequences. Because remember, what we're doing here is we're counting the probabilities, and then we're sampling for each iteration. We're sampling randomly based on the weights given by the probabilities in the probability tables. So everything is each of these motif positions are somewhat randomly chosen, but they are chosen in such a way that you choose them based on some kind of probability weights. So it's not perfect because there's some kind of element of randomness. And if you have an element of randomness, then sometimes you may miss the most optimal probability. And so often or sometimes you may not obtain the optimal motif positions for all of the sequences. But it's not always that bad, because since you're randomly sampling and you're not always strictly sticking to the probability weights, then you can sometimes avoid local minima problems or complications, because remember, if we don't sample randomly and we just choose the motif position, we just sample the motif position with the highest probability, then there are chances that we may meet some local optimum or local minimum problems and get stuck there in the local minimum. And so by randomly sampling, we are sometimes able to avoid these local minimum problems and thereby reach the global minimum or global optimum motif positions. Now, another bad thing about the Gibbs sampling is that you have to specify an estimate of the width of your motif, because like for instance, for the example here, we gave the algorithm an estimate of 7 residues as the length of the motif. So this is one disadvantage of the Gibbs sampling method, because you have to provide an estimate of the motif width. And then but a good thing about the Gibbs sampling method is that it's a very iterative process, and each of these iterations you can actually inspect how the probability tables look like and how the motif positions move during the iterations. And sometimes the final convergent answer may not actually be the most optimal result, and sometimes you have to look up the suboptimal results or the motif positions from the previous iterations, and maybe some of those previous iterations would have motif positions that visually look better than the actual convergent answer. And so here, the Gibbs sampling motif gives us a way to inspect the previous iterations and thereby visually check or manually check if there are some supposedly suboptimal results that are actually the best results. And one more good thing about the Gibbs sampling method is that it runs in linear time. Your n here standing for the number of sequences. And so for this presentation, my main reference was this here. I used the example from this lab over here by Blekas. And I also consulted this review paper by Ruchka, but the original paper is really from the original paper for the Gibbs sampling method is really by the Lawrence in 1993 in the science paper. So if you want to look at the original, look at it, Lawrence 1993 Gibbs sampling for motif detection. But this paper here is it simplifies the whole the discussion for the Gibbs sampling. So you may try to look this up here to understand the notations, and there's actually an example here, a quite elaborative example on the Gibbs sampling method, and I would recommend that you read this simplified article on the Gibbs sampling method. Thank you very much for listening. I hope you learned something.